Okay, so next we see section 7.3, sums of non-negative numbers. Precisely, we are going to consider infinite series whose terms are non-negative real numbers. So this is how Professor Tao starts things off. We now specialize the preceding discussion. That means we have already seen in the previous section the basic convergence theory of infinite series. So that discussion we are now specializing to consider sums, that is infinite series, which look like this, where these ANs, all the ANs are non-negative real numbers. And this situation comes up when you consider the absolute convergence test, because there you have to consider this series where these terms then become non-negative, because absolute value of any real number is a non-negative real number. And if it happens that all these terms are actually non-negative real numbers, then there is no distinction between absolute convergence and conditional convergence. So let us now see what can we say about this special class of series where everything is non-negative. Now we no longer have negative terms like what we had in that result, that alternating series test. Now we no longer have that type of terms. So we start off with such a series if the terms of the series summation of an as n varies from m to infinity. M is of course some integer. If the terms of the series are all non-negative, real numbers, then the partial sums actually, Sn, which is defined to be equal to the sum of this finite series, are all okay. Let us also just mention the point, the stage from where capital N should start. Then the sums are increasing. That is, Sn plus 1 is greater than or equal to Sn. And this fact one can of course prove by induction on n, and you can clearly see why this is true. It's because of non-negativity of the terms an. The more terms you add, the higher partial sums you get, but in doing so you are adding non-negative real numbers. So if the real number an, that is this an that you are adding to get the next partial sum, if that is 0, then Sn plus 1 becomes Sn. Otherwise, Sn plus 1 is strictly greater than Sn. okay, that is the sequence of partial sums, that is this sequence, is an increasing sequence of real numbers. These inequalities, of course, I hope you understand. Since Sn plus 1 is Sn plus An, sorry, it's not An but An plus 1, and An plus 1 is greater than or equal to 0, it is non-negative. All Ans are non-negative, so that is why this is greater than or equal to Sn. So that's how we are getting these inequalities, and that is why this sequence of partial sums is an increasing sequence of real numbers, a monotone increasing sequence. And in the chapter on sequences of real numbers and their convergence, we already have seen precisely when such sequences are convergent, namely when they are bounded above, they have an upper bound, that is, there is some real number such that all the terms of this sequence are less than or equal to that real number. And we in fact have seen much more than that. We saw that in that situation the sequence will actually have the limit which is the least upper bound of the sequence. So we can now refer to those results and write the corresponding criterion for convergence of this series, because its convergence is by definition the convergence of this sequence. So that's why we write from proposition 638 and corollary 6.117. 6 means it's that chapter on sequences of real numbers. The 7th one is where we are right now. It's about series. So by these results, we thus see that the sequence Sn is convergent, and hence the series is convergent if and only if it is bounded above. Bounded above, bounded from above, they mean the same thing. Oh, so okay, the author has written about an upper bound. We can in fact continue from here also, that is this is convergent if and only if there exists a real number m such that Sn is less than or equal to n for all n greater than or equal to m, that is all the terms are none of them exceeds m. So if that happens, then Sn is convergent, and hence our original series is convergent. And if our original series is convergent, that means if Sn is convergent, then there should be one such upper bound. And now we can of course summarize this entire thing. This now becomes the criterion for convergence of that original series. So we can now summarize that as a result. And that is this proposition. This is the first item of this section, so 731. Oh, I can almost not write anything else here. At least let me write let. Let this be a formal series of non-negative real numbers, that is this for all n greater than or equal to n. Then this is convergent. In fact, not just simply convergent, but we can add absolutely convergent, because we are dealing with non-negative terms, and we have already mentioned that in that case absolute convergence and conditional convergence do not have any difference between them. But still, just let's mention absolutely convergent, because that is stronger than conditional convergence. Although in this case there is no difference, but still this is absolutely convergent if and only if there exists a real number m such that these finite sums, or these okay, I have got the habit of writing infinity immediately. These sums are all bounded from above by m. And let me just complete writing this statement, then I will say something about a possible confusion that you can get at this point, such that this for all n greater than or equal to m. Okay, now sometimes when we are thinking very fast and when we are not very careful, we may not inadvertently, of course, not knowingly, we may not distinguish between these two things. So the criterion that these finite sums should be bounded above by m suddenly will become something like this. You are thinking about the series and you see that it's a series of non-negative real numbers. You don't see any minus sign. All the an's are non-negative, and this boundedness may be confused with this boundedness for all n greater than or equal to m. This is an entirely different thing. It's not this thing. Okay, these terms themselves, they may be bounded and the series still may be divergent. A simple example is this. Which of course is this infinite series. So all the terms are non-negative, in fact all of them are positive and they are bounded, but the partial sums themselves are not bounded. In fact, the partial sums for this series are just the positive integers. If you think about it, the first term is 1, the second is 1 plus 1, the third is 1 plus 1 plus 1 and so on, and this of course is not bounded and in fact it is divergent, and that is why this series is divergent. So do not confuse between this thing and this thing. So that is the proposition. It's a very simple one. It's just almost a what can I say? It's the restating facts that we already know about convergence of monotone increasing sequences. But anyway, for a series of non-negative real numbers, now their convergence comes down to the question of whether their partial sums are bounded above or not. And this one has this proposition has a nice corollary. There is of course no need to prove this proposition because we already, the proposition is simply a summary of what we concluded before it, which comes directly from those sequence results. But this corollary, next corollary has to be proved, which however we will do in the exercises. And it has this name, comparison test. It's about comparing two series of real numbers, and the convergence of one of them will imply the other is convergent, and in fact absolutely convergent. Let this and summation bn p to formal series of real numbers such that there is a condition the absolute value of an is less than or equal to bn for all n greater than or equal to m. Okay, so that way the corresponding terms of the two series are compared. They are related through some such inequalities. In fact, not just ordinary an but rather absolute value of an. So this type of inequality you already know. This is equivalent to this thing. So it's not simply the statement that an is bounded from above by bn, but an is also at the same time bounded from below by minus bn. And something else is also there in these inequalities which may not be immediately apparent. Note that because the absolute value of any real number is non-negative. So, because these inequalities are part of our hypothesis, so these bn's are automatically non-negative real numbers, and that is why among these two series, the second one is a series of non-negative real numbers. Okay, let us complete the statement now. If the second series is convergent, then the first series is absolutely convergent. And in fact, the sum of this series which you get from the first series by considering the absolute values of all the terms, or which is the series that you consider when you try to see whether this is absolutely convergent or not. So we are saying that if this is convergent, this is absolutely convergent, which by definition means that this series is convergent. So its sum in fact is going to be less than or equal to the sum of the second series. So this part is extra. We are not just simply saying that this is absolutely convergent, but rather that this is less than or equal to this. And its proof, there is of course, okay, we can in fact, there is one more term in this. It's not simply one inequality, it's actually two inequalities. We can mention that other one also. So the thing here is that, you see, when we defined absolute convergence, we also proved one result, you recall in the previous section, that if a series is absolutely convergent, then it is also ordinarily convergent, that is conditionally convergent. And in that result, we proved some inequality like this, that is the absolute value of the sum of the ordinary series is less than or equal to the sum of the, if you want to call it, the absolute series. And now we are also saying that this is less than or equal to the sum of the second series. So this part we are just simply bringing result from that previous section, and this is something we are saying here which is new. So this is the full statement. So let's just go through it once more and see what we have written here. We have two series, both of them are infinite series of real numbers, and there are inequalities or relations like this linking the corresponding terms of these two series. From these inequalities we automatically see that the bn's are all non-negative, so the second series is a series of non-negative real numbers. Now if this second series is convergent, then the first series is absolutely convergent, which means this middle series is convergent. Now what we are saying additionally is that the sum of this middle series is going to be less than or equal to the sum of the second series. Okay, and this part is coming from previous results from the previous section, and its proof is the first exercise of this section. So we will do it afterwards. Now this comparison test we can use just like this, or we can also use it in the contrapositive form. So notice carefully what we are saying here. We are saying that if this is convergent, then this is absolutely convergent. What is the contrapositive of this statement? If this is not convergent, I mean not absolutely convergent, let me write it down, that way it will be more clear. This is convergent implies this is absolutely convergent. What that really means is that this is convergent. Its contrapositive is this series is not convergent implies this series is not convergent. This series being not convergent means this is not absolutely convergent, I mean our original first series. Okay, so in that way also we can use this result. So sometimes the comparison test will help us show that some series are absolutely convergent, and sometimes it will also help us show that some series are divergent. We can, so that's what a professor is saying, we can also run the comparison test in the contrapositive. Okay, so which is just this: if we have these absolute values of an less than or equal to bn for all indices n greater than or equal to m, that means for all indices, and summation an is not, it has started raining, absolutely convergent, then our second series is divergent, which the author has decided to write absolutely conditionally divergent. There is no need to put the word conditionally before divergent, it just simply means the series is not convergent. But anyway, Tau writes like this: is okay, so that way also we can interpret this result. And again I am reiterating some things every now and then. Again I am saying, between the statement and the contrapositive there is a high chance of confusion and interpreting things incorrectly, so be careful with that. One source of error would be to forget about the direction in which things are going. If summation Bn is convergent, then summation An is absolutely convergent. If that, again reformulating it in terms of contrapositive, that just simply means if summation An is not absolutely convergent, then summation Bn is not convergent, that means divergent or conditionally divergent. That's the thing. Okay, so fine. So we have got one nice test, comparison test, to see which series are absolutely convergent and which ones are not. So if you are given a series summation An and you want to test whether it is absolutely convergent or not, and you want to use comparison test, you will then need a second series Bn. So many times there is a very nice candidate for this second series, and that is your well-known geometric series, whose convergence is also well known. So a useful series to use in the comparison test is the geometric series, and this next result is about the convergence of that class of series, that is geometric series, which is lemma 733. In fact, in most elementary courses or elementary treatment of these things which you encounter even on school level, infinite geometric series is the class of series that you encounter first, and where you see that there is a notion of convergence. So this is familiar to all of us almost. Let X be a real number if the absolute value of X is greater than or equal to 1, then the series summation x to the power n, where n varies from 0 to infinity, is not convergent, that is, it is divergent. So this is their familiar geometric series. When you learn about geometric progressions in school, you then come across those notions, the notion of common ratio. So in this case, the common ratio you can clearly see is x, and there is one corresponding notion also, that of arithmetic progression, where you have common difference, because this is not convergent. On the other hand, if the absolute value of x is strictly less than 1, then the series is not just convergent, it is absolutely convergent. That is one thing. And we also know what the sum of this series is when it is convergent. It is the reciprocal of 1 minus x. This also we will prove in the second exercise. Okay, so all of these are very nice, but they are somewhat basic, very basic. Now we mention about a result, which of course we will prove, but not in this video, which goes slightly deeper than these basic things, and which will be very useful for us. It will ultimately tell us something, the convergence or divergence about a large class of series which are not geometric series, they are something different. So this next thing is Cauchy criterion. Augustin Louis Cauchy, he found this. Hopefully, if Cauchy's name is appearing, that automatically does not of course mean that Cauchy found it, because this naming, there are many things. You will find results, concepts named after some mathematicians who actually had nothing to do with them. You see the history of mathematics and the history of these things, you will see that it's not really that straightforward. There are many factors involved in naming something. So if time permits, and time actually is not a factor. At one stage we will discuss about those things also, if the situation arises. Okay, so we now give a useful criterion This naming does not follow any hard and fast rules, and sometimes the situation is so bad that things have been named after someone who, later on, things have been named after someone who at the time of discovering those things were not, they were not even born. You just see how, you probably already have heard about this things, Taylor series, Maclaurin series. You search for these things and you see how the names came to be. You will realize what I am talking about. Known a very useful criterion known as the Koshi Criterion. So let's just see the statement of the proposition, and the proof we will do in the next video. So this will be item number 4. Let an, where n is varying from 1 to infinity, be a decreasing sequence of non-negative real numbers. That is, an is greater than or equal to 0, and we have to then say what decreasing means. And an is greater than or equal to an plus 1 for all positive integers n. Then the formal infinite series is convergent if and only if it's an equivalent condition. This series is convergent. 2 to the power k times a2 to the power k, where k varies from 0 to infinity. Let's just see some first few terms of this series. If you put k equal to 0, then here you get 1, here also you get 1, so a1. For the next term you put k equal to 1, so that gives you 2, so 2a2 plus 4a4 plus 8a8 and so on is convergent. Okay, so what we are saying here is that we have a series like that where the terms are not only non-negative but they are decreasing. Under these conditions, the original series is convergent if and only if this series is convergent, which has terms of the original series but not all of them. It has precisely those terms where the suffix is a power of 2. That is, we are actually not considering all the suffixes which are positive integers, a1, a2, 1, 2, 3. We are not considering all of them, but we are considering a subsequence of that sequence whose general term looks like this, 2 to the power k. So it is a little it's somewhat amazing to see that we can in fact not consider many terms of the original series and consider only these terms where the suffix is a power of 2, and we form this other series using only those terms. Of course there are infinitely many of them, but infinitely many of the original terms also we are not considering. But in spite of that, just this much is enough to say whether the original series is convergent or not. So this is Cauchy criterion. And one more thing is that this is not just simply removing some terms of the original series and we are getting this series. We have additional things multiplied with these things. Okay, so that also has to be taken into account. Now in the next video we will prove this, and a corollary of this Cauchy criterion will let me just mention that. A corollary to this Cauchy criterion is about the convergence or lack thereof of this class of series. Okay, this is not a geometric series. Here p is a real number and the n is changing. Okay, n varies over the set of positive integers. So the series, if you write it in that form, it looks like this. And using Cauchy criterion, we will be able to state and prove a result. State, of course, we can just simply state it, but we will be able to prove that this series is convergent when p is greater than 1 and divergent when p is less than or equal to 1, which will immediately give us some examples. One example in particular that we already mentioned before is the harmonic series. If you recall, at one point we mentioned that the series where the terms are reciprocals of positive integers is a divergent series, and that series has the name harmonic series. So its divergence is a direct result of this corollary that we will see. So the harmonic series is this, which we obtain by putting p equal to 1 here. In that case, in these cases, the series is divergent, so the harmonic series is also divergent if you assume this result for now. So this is a series which we used as an example to demonstrate the fact that there is this condition which we already proved is a necessary condition for convergence of this series. If this series is convergent, then this limit exists and is 0, but it is not a sufficient condition. So as a counter example, we mentioned this harmonic series where the terms actually, as a sequence, the terms are approaching 0, they have the limit 0. but the series is divergent. So this is a very peculiar thing if you really think about it. If you consider the partial sums, that is 1 plus 1 over 2, then 1 plus 1 over 2 plus 1 over 3, then it seems like things should settle eventually. That is because you are of course adding positive terms, so the partial sums are increasing, but it feels like things should settle because the thing that you are adding itself is diminishing. It is getting reduced. It is going towards 0. In spite of that, the sums are not bounded. They increase at a very slow rate, but still they increase, and they, if you consider the partial sums of this series, it can be shown without using this result but directly that the sums in fact exceed any real number. Of course, if you take a very large real number, for example 1000, then you will need many terms of this series to form a partial sum that is greater than 1000, but it will happen. Okay, so that is the nature of its divergence. Okay, so that is fine, but where am I going with these things, and why am I saying all these things somewhat way ahead of time? That is because you may know that this thing has a generalization. The P that you see here in this case of course is real, and in this text we are going to consider only real numbers. Only in the second volume at one stage while discussing trigonometric functions we will mention complex numbers, but if one allows this P to be complex, then one gets a function of P. That is your famous Riemann Zeta series. Probably I should not say Riemann Zeta function. Now this function where P is a complex number mysteriously is related to prime numbers and their distribution, and regarding this connection and some other related things, Riemann made a conjecture. He said that for those complex numbers P for which this zeta value is the C, this zeta of P that I have written here is actually not the entire thing. There is some analytic continuation and some things are there, but that function which a part of which is this, that zeta function becomes 0 for some complex numbers. Now negative even integers are some such points which you put here, you will get 0, but there are some non-real complex numbers, so those are non-trivial zeros of the zeta function. The conjecture that Riemann made is that all those non-trivial zeros lie on this line, that is which is halfway in between these two vertical lines in the complex plane. That is the Riemann hypothesis, which is one of the most unsolved, most important unsolved problems in mathematics. So it will be mentioned by the author also in one remark, so we will see these things. This of course is still well beyond almost everyone's reach. Almost everyone's means everyone's reach. So many things have been tried but no one has been able to do anything with this. There are results, of course. For example, I think Godfrey Harold Hardy proved that infinitely many zeros actually lie on this line, if I am correct, but not all of them. So that's where things are still open. But it follows from some functional identities on zeta function that all the zeros do lie in this critical strip. This is called critical line. The critical strip is the region lying between these two vertical lines, 0 and 1. That has been proved. Okay, so all the zeros lie here, but they have to lie here. Numerical evidence is overwhelming, but still, because there are infinitely many, actually there are infinitely many zeros, so a computer will never be able to prove this. We need a solid mathematical proof or a counterexample. Generally, it is believed by mathematicians, given the overwhelming evidence, that it is true, but still a proof is very far away. No one knows. Okay, so with this I end today's video. So if you want to say something about these things, you can write in the comment section below, or you can mail me at my address, which will, the link will be there in the description. And tomorrow we don't have any upload. Day after tomorrow, that is on Tuesday, we are again going to group theory from Herstein's topics in algebra, and this time there we are going to start solving the exercises on permutation groups. So with that, I wrap things up. So see you on Tuesday with group theory problems. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.